And now to tonight. We'll be hearing from Ken Scambler and Robin Doherty on the focus of functional programming, experiences in the real world. So let's get started. Ken Scambler is a long-time functional programming enthusiast based in Melbourne. At REA Group, he mostly works on Scala microservices, mentors new Scala programmers, and fosters the contagion of FB. He is known for rote learning the curiosities of legacy systems and writing lengthy, therapeutic blog rants about them. He can be easily trolled by using the word isomorphic incorrectly. Did I say it right?
Yes.
Kind of? Don't ask me what it means. So, please join me in welcoming our first speaker, Ken Scambler.
Thanks for coming, everyone. So I work at REA Group. We make the website realestate.com.au that you might have heard of. A bit more about me. I've been doing Java for ages. Scala I picked up about 5 years ago and started learning about functional programming at that point in time. I've done various bits and pieces of C++, Haskell whenever I can because it's really cool. I don't mind Clojure and various Lisps, and every now and then when I have a gun to my head I have to use various scripting languages and so forth. That's my CV. So at REA, we've been using Scala, which is a functional programming language, for over 2 years now, and we have 3 teams. We've got over 17 code bases in production now, totaling about 43,000 lines of code. And this has been enough that we've learned a bunch of lessons, we've done a bunch of things wrong, and we've done a bunch of things right. And so I'm going to take you on a bit of a story about that and why we decided to do functional programming at all, why we picked up Scala, and how we went about introducing a new technology and that sort of thing. So first of all, just briefly, why functional programming at all? So because it is good for software is the answer. If you're not familiar with it, functional programming is where you program using pure functions like you would have in mathematics, where they essentially just map inputs to outputs such that the same input will always produce the same output. And as it happens, this ends up being a really robust building block for software. And unfortunately, it seems the benefits of this are underappreciated. And so the discipline of functional programming uses this as its foundation. I want to talk about a little bit about modularity, abstraction, and composability. These are all really important things for software engineering, not just functional programming, but functional programming enables them in a way that other paradigms don't to the same extent. So first of all, modularity. By this I mean being able to reason about one piece of code by itself without having to fit the entire world in your head. Often when you're maintaining some code, you'll find that you can't just look at it by itself. You have to look at the thing it talks to, and the thing that talks to that, and the thing that talks to that. That's bad modularity. Because functional programming pushes side effects to the outside of the program, it's a lot easier to look at one piece of code by itself. Abstraction. Some people think this is maybe a bad thing because it makes software more complicated, but in fact it's the complete opposite. Abstraction is about saying only what you need to say and knowing only what you need to know. Functional programming lets you write more abstract code, which means you throw away rubbish that you don't need. Details that are completely irrelevant to what you're doing, you can throw them away, and this makes your program simpler. It makes it more reusable. So this is a clear benefit. Composability. Now this is important in any piece of software. And by composability, I mean when you can take 2 elements of your program and combine them together into one element in such a way that it doesn't become more complicated. You end up with the same kind of thing as the 2 things that you combine together. And when you write composable patterns in software, it means that many pieces of your software can combine without becoming more complicated. And this is really important. Functional programming enables this too. So ultimately, all these things are just about simplicity. Simple software. That's what we're gunning for here. So this is why we've embarked on this journey. But good technology isn't enough. because we're all humans, we're all inexact, we're all made of flesh and blood, and writing software in a team is a complicated process that can fail in 100 different ways that have nothing to do with the best technology in the world. And so we need to do a bit more than just have good technology. So firstly, to talk about the messy human context that we operate in, I'll need to tell you a bit more about our organisation. So we make realestate.com.au, but what you may not know is we make a bunch of other stuff too. There's a commercial website, there's a Chinese one, there's an Italian one, and a few other ones around the world. The development team is split between Australian developers based here in Melbourne and a ThoughtWorks China team in Xi'an, in China. Each team is sort of split between these two bases. Sometimes there's a small group in Melbourne and a larger contingent in Xi'an. Sometimes it's split 50-50, and sometimes it's totally in Melbourne. It just depends. It's not a cost-cutting measure, as some offshoring arrangements are. Really, it's more just about flexibility and just being able to get lots and lots of people onto a job quickly, depending on where the work's at a point in time. They're very good, but it's still hard making it work. We need a lot of communication, a lot of investment to make it work. It's not a cost-cutting option, it's because we want to work like this. And that's part of the human background of what we're doing. Another big deal culturally is bottom-up tech decisions. So we don't have some big kahuna that hands down the one true way to do things. The people who are best placed to know how to choose the technology are each team. So if one team wants to use Ruby, they're a Ruby team. Another team, fine. Java, yep, cool, they're a Java team. If they want to upgrade, they can be a Scala team too, so that's good. This is what we don't do. So we have the architect on Architect Mountain who decides on the one true language for everyone to use, and all shall perish who oppose. No. We don't do that. Each team, they are the people that are best placed to know how to choose the technology. So that's important. So if you want to introduce a new technology, like functional programming or Scala or whatever, you need to win hearts and minds. That's the only way to do it. The software background of the organisation, well, we're refugees from the first wave of dot-coms in the 90s, so there's a substrate, a geological substrate of Perl code. Eventually, I mean, you got to do what you got to do if you're a startup, but we won't judge. But eventually, the consultants came in, cleaned up the place, brought in a whole lot of Ruby and Rails, and so was born the Monolithicene epoch. Big Ruby on Rails, Java enterprise code bases. But big monolithic code bases, they have problems too, as no doubt you're aware. We'd have maybe 5 teams feeding into the one giant code base, and you can't release software without impacting everyone else. And so we'd have one release a month, and the entire company would go into lockdown for a week before each release. It was disastrous. We had to change. And so now we live in an amazing future city of microservices, where each team is really independent, completely independent from other teams. Everyone can release software really, really regularly whenever they need to. And it also means it gives us a lot of freedom in what technology we choose, because each microservice can be whatever technology, it doesn't matter. They're all communicating with HTTP and whatever anyway. So this is the ground, this is the background into which we adopted FP. So in 2013, a bunch of us in one of the Java teams, we've got a bunch of big code bases and things, and we're thinking this is getting a bit hard to manage. Bugs are just getting out of control. What are we going to do? Some suggestions were made. Not all of these suggestions were successful. And so we thought, okay, we've heard that functional programming is a good way to do things. Let's try this. And so, righto, let's do it. And so we tried to write Java in a more functional way by eliminating mutable state and writing pure functions and separating side effects and that kind of thing. But that's really hard to do in Java and most mainstream languages. It's hard. So the FP part was great. We got real benefits from that in our code, but Java was still a big facepalm with trying to make it all hang together. So one of us decided to carve out a big piece of the, a chunk of the monolith. It was our login and registration system, and rewrite it in Clojure. Just a quick spike. And this is really good. Everyone sort of, by having this concrete code base, everyone sort of got onto that and go, yeah, that's really good. There's a way forward. We can get out of this. And so that was completely successful in convincing the team to adopt Scala. Now, there's nothing wrong with Clojure, but Scala was better for us because we value static types as a way to improve code quality and to write robust software. And it just made sense for us. And also we had people on the ground who were really good at Scala and nobody really knew Clojure. So that made sense for us. Other people can choose other languages, that's fine. So that was the first project we did then, was writing that in Scala. And so we had a team of people, partly in Australia, partly in Xi'an. We had a Scala guy in Melbourne and a Scala guy in Xi'an, using the Play framework, a bunch of other stuff. And we needed to teach people how to use this because all the people especially the people in Xi'an hadn't used Scala before. And so we had a sort of a mentor system where the people who had used Scala before would mentor the other programmers and do code reviews. And that worked okay. So the result of this, it was a steep learning curve, but it was okay. We got a good tech result. Frameworks, the Play, it's one of these big nanny frameworks that wants to be all things, and we found that a bit heavy for what we were trying to do. But yeah, it was a good thing. Good feeling. It was a success of a project. So time went on. Another team picked up Scala as well. We'd got a few more things under our belt, and the next project we did in that team, we tried some different frameworks to mix things up a bit. We had 2 Scala experts in the Australian team and none in China. And this time though, we were kind of busy and we made almost no effort to teach the people in Xi'an how to use Scala or functional programming. And we didn't mean to, it's just, you know, it's busy, everyone's got stuff to do, and we just didn't get around to it, and we really paid for this. The learning curve is significant. If you're picking up a new language, and especially a new way of thinking, you need training. And so the technical result, it was okay, but it needed rework. But most importantly, the sentiment was not great. The people that hadn't been trained well enough, they felt kind of abandoned and thrown to the wolves, and rightly so. And the lesson from this is, if you're picking up a new technology, and especially one that requires thinking about things in a different way, you need to invest in your people. You just can't skimp on that. Another example of a project then. So we've got this lesson under our belts. This time it's an Australia-only project, which simplifies it to some extent. We had 2 Scala experts this time. Now we changed things up a bit with the frameworks again, nothing too controversial there, but we decided to try out a new technique called monad transformers. Now I'm not going to explain how these work. It's a technique from functional programming that's popular in Haskell. And basically the idea is you express the concerns in your system in the type signature of what you return in a pure functional way. And then there's a thing that happens at the end where it sort of unpacks that type signature one layer at a time and actually does the things that it needs to do. So we had 2 mentors on the ground teaching people, but it was really hard. And what we found was, with a team of experienced engineers, we couldn't teach it to them in the space of a project. We got an okay technical result in the end, but the sentiment was kind of mixed. And it became clear that if we're going to expand Scala use in the organisation, we couldn't use something that was going to leave people behind. So that's just a thing that we learned, and we had to react to that and change. One of the things that you sort of find with a lot of the different specialised areas of expertise of the organisation, you get something like this, where you get a small number of gurus at the top who really, really know what they're doing. And then a broader base of all-rounders who can sort of get in there and do stuff, but then, you know, they don't know everything. And then a bunch of people who don't know it at all. And so DevOps is like that. Front-end code, it's a bit like that as well. AWS, same deal. This is what it looked like when we started Scala. We had two gurus and no one else knew anything, and a broken rickety ladder. Fortunately, we've really invested in learning now, and it looks a little bit more like this now. We still need more people especially in the all-rounder category, and certainly more in the guru category, but we're getting there. We can't leave people behind, though. We have to get as many people onto one of these platforms as we can. That's our biggest challenge. So this was sort of our lesson. Now you can always stick to familiar concepts. You can stick with Java or Ruby or JavaScript or whatever, and you're not going to face a learning curve at all. But you're setting a really low ceiling for what you can achieve as a team by not taking on new things. But if you can't make a concept learnable, then you kind of can't use it, because ultimately only a couple of people will understand it, and it'll end up getting rewritten anyway. So that was sort of our lesson from that. So up next, one of the Ruby teams decided, okay, let's try Scala. We're struggling with Ruby. Let's give Scala a go. And so they started using it alongside their existing Ruby stuff. Now, so this is now in mid-2014. A fair amount of time has passed now. So they used a similar kind of tech stack to what we used in the first place. Mixed team from Australia and Xi'an. But you'll notice none of them had done Scala before, or functional programming. And so learning was a real challenge. Their main source of learning was trial and error and doing code katas and project Euler problems and this kind of thing. But that was kind of a challenge. Now, so the learning curve for everyone was really, really steep, and they had a lot of frustration in hitting obstacles that, had they had someone more experienced in that technology on the team, they wouldn't have had to go through that pain. So it wasn't a disaster. They sort of got through it. It wasn't as good as it could have been, and the sentiment was mixed. There was a lot more frustration than there needed to be. And this is the lesson from that is, it's really hard learning from scratch. It's not impossible, and I don't want to put you off it, but just be prepared for pain up front. It is genuinely harder than if you've got someone there embedded who can teach people and can explain how to do things without learning lessons that you don't want to have to learn the hard way. So more and more code, and so many iterations. We learn from all our mistakes, and we get better and better and better. And so our latest project looks a bit like this. There's a bunch of design trends. As we've gone more and more toward pure functional programming and away from object-oriented programming. Inheritance and mix-ins we've discarded in favour of just having static functions, because the whole point of inheritance and subclassing is to put flexibility into your software so that you can swap out the functionality of methods. But we found that the type signatures of the functional techniques we used gave us all the flexibility we needed. And so we could just have static top-level functions and not have all these classes and subclassing and inheritance and that sort of thing. Partial functions. So a partial function is one that doesn't have a defined output for every input. So for instance, getting the head of a list. If it's an empty list, there's no head. You can't do anything. It'll blow up. So this is not a total function. It's not even a function at all in the mathematical sense. It's something that could throw an error. But you are choosing to use a partial function, and you can write software without partial functions. And if you do that, you won't get runtime errors. You can choose not to have runtime errors. So this is how we went. We went more and more towards completely total functions, so that we just don't get null pointer exceptions or runtime exceptions or array overflow, these sorts of things. The type system forbids it. So this is a good thing. Exceptions are a side effect. they're a nasty side effect. They're like a fancy kind of go-to, and people use them really inappropriately, it seems, for recoverable things, for things that are really part of what you need to understand about a function. So for instance, you try and authenticate and it'll either succeed or it'll fail, but the success case is a return value and the failure case is an authentication exception. This makes no sense. It's the type system is telling a lie because it's saying that it returns an authentication or something, but in fact it may or may not do that. And so rather than use exceptions, we use something called sum types, where we say the type of this thing, it could be this, or it could be this, or it could be this. It could be a success, or it could be a failure. And then when you use that value, when you consume that value, you need to fold over those possibilities and say, well, in this case, if in the case it succeeds, I'll do this. In the case it fails, I'll do that. And this makes the software much, much simpler without exceptions bouncing around all over the place. And also, strings and primitives, you can get a real benefit from not using these raw types because they're not type safe, because they describe so many possibilities, so many more possibilities than are really required by your software. Usually the average use case of a string is a very constrained thing, like an email or an identity, or a user ID or a URL that has actually a very limited number of valid cases, and not the complete works of Shakespeare. And so we use wrapper types to constrain the possibilities for even very, very simple things. So we very, very rarely use strings unless it's genuinely free text. So these are sort of the design trends that we've moved more and more towards as we've gone and become more comfortable with the techniques. We run a functional programming guild once a week, and importantly, this is in work hours. It's not at lunchtime, it's not after hours. This is an investment in our people. It is part of the job. So, yeah, we get about 7 to 12 people turn up each week, and we have talks, exercises, reading, just whatever people want to do. It's been really successful, and it's created a really good feel and a good community within the organisation of people that want to learn and can teach other people as well. So our most recent iteration now, on this project we had 2 Scala experts and a bunch of people that hadn't really used it before very much. And this time we doubled down on learning. We knew we had to. And so we had 2 mentors, we did pull requests, code reviews, pairing, the FP Guild once a week, and the result of all this investment was a great success. For the organisation of the software, we used a technique called free monads. And this sounds like another one of these sophisticated Haskell techniques that's going to blow everyone's brains away. But in fact, it was actually a complete success. And we've had really, really good success in teaching people that had never used Scala or done any functional programming before this concept. So through trial and error, we found something that had really good technical benefits and was easy to teach as well. So the report card, the learning curve was actually really smooth because of all this investment. Productivity was great and everyone was really happy with it. To explain the concept a little more of the free monad technique, without getting into the nuts and bolts, of course, it essentially means that we're writing all of our software, or at least all the bits that we care about, all the logic and all the decisions in a big pure core, but rather than doing the side effects in place, it actually builds up a script containing instructions describing what it wants to do. So the script will say, I want to authenticate, I want to use the config, I'll get this thing from the DB, and that thing that I got from the DB, I'll change it and then update the DB and log the result. But none of this happens in place, it just builds up a big script of instructions. And so the output of that entire program is this script. And so we have an interpreter that sits outside the program, or rather at the very end of the world, that is actually performing all the effects. It just knows how to perform each command. And that's connected to a real database and the real external services and blah, 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 all these things it needs to talk to. And this makes the software so much simpler. When we test it, we can just provide a pure interpreter. The software as a whole doesn't have to change. We don't have to swap anything in. We don't have to have mocks and stubs and pretend things. We can use the software as it is, just interpreting the script in a way that enables us to test it. The tests then are just input, output, assert. There's no messing around with, then I did this and then I did that and then I did a pirouette and then I jumped through a hula hoop and then all these made up stories that you have to do in your average object-oriented test suite. And then in addition to that, we have a very, very small number of wafer-thin end-to-end tests where we have a real-ish interpreter. There's some things like things that are, SQL queries and the like that are difficult to test in a pure setting. And so we have a small number that just do this. And again, it's just input, output, assert. These kind of tests tend to be fundamentally more expensive and unreliable. So we have only a small number. And that works pretty well for us. So this is what it looks like, the code in practice. We've got a top-level object. So this is essentially a static function. Get list, it takes a user ID and it returns not a response, but a script of response. But you can see the code here, it's just this completely declarative, regular, imperative program. It's saying, get me the searches. It's not really getting the searches. It's just saying it wants to get the searches. So given the thing that we would get if we were getting the searches, then we get the config. And you see here, we don't have to thread the config through here at all. We don't have to worry about dependency injection and all that wiring and have wiring logic spread throughout all the code. That's something for the interpreter to worry about. So we can just say, well, yeah, given the config, given the stuff we get out of the database, given the stuff we want to do to it, then we'll just return the response we want to return down here.
Okay.
Yes.
Have you done a performance test on this? 100 users, 200 users, what is it like when you have...
It's fine.
It's fine?
Yeah. Now, because of the indirection involved in the technique, there is a speed penalty, but it's insignificant for what we're doing. We're not doing high-frequency trading. In practice, in our network of microservices, the real question of performance is in latency, in network calls, and if we really wanted to speed things up, it would be more like doing asynchronous I/O and that sort of thing.
Yeah, because everybody's sharing the code. So how does it work? Does it transfer a copy of the code into the memory, and then you process it, and then when you finish, you just let go?
I'm not sure what you mean.
In Java, you just load it into
It compiles down to JVM bytecode, just like a Java program does. This is just an alternative. Scala is just an alternative text language that compiles into that same bytecode that runs on the JVM. Yeah.
So you never done any tests, like 100 users, 200 users, and then concurrent users, and then you test the performance?
Yeah, we do volume. We do test load because depending on what we're doing, we get very significant load. But this is not a problem performance-wise. Yeah. The squiggly arrow down the bottom, that's just a thing, that's the web framework that we're using has that as a way of cobbling together response codes and that sort of thing. So that's what it looks like. The learning curve was really, really smooth. The adaptation from PowerPoint was apparently not so smooth. No mocks. No stubs, no flaky pretend servers just to check a response code. Gone, all gone, we don't need it. Flaky tests that take 30 minutes to run, all gone. Anyone got one of those? I reckon some of you might. Side effects everywhere, nah, all gone. Don't need to worry about it. No exceptions, no runtime errors, no intrusive DI frameworks. And the result of all this fancy technology and functional programming is our software is simple. Most business software has no right to be complex. If you're just putting stuff in and out of databases and writing CRUD apps, and unless you've got, like Google-like scale, it's not rocket science, and it has no right to be complex. It's simple, and the implementation should be simple, and that is what we're trying to achieve here. You shouldn't be dealing with all that complexity and crap just to do the same thing that everyone's doing in every other business. There's a better way. Now, FP has got a lot of concepts. It's a very, very deep subject area. It's a very, very tall tree, and you can keep learning and learning and learning, and you'll never reach the top. There's just so much to learn. But there is so much low-hanging fruit. You can benefit from the techniques of functional programming almost immediately from using them in your code. Thank you for your time.
All right. Robin. Robin is a programmer with software consultancy ThoughtWorks. He makes a living by dealing with complexity. He wishes everything were simpler, especially code. Please join me in welcoming Robin Doherty.
Hello everyone. Thank you for having me this evening. So I'm here to talk to you about introduction of functional programming at IWF, which happened about 2 years ago. IWF is the 4th biggest superannuation fund in Australia. They have $120 billion in management. They have 700,000 customers. So like a lot of enterprises, they have a lot of old software. They have a lot of legacy systems with which we had to work. So I was a developer there for about a year. This was in 2012 till 2014. And I was tech lead for about another year on the latter half of the project that I'm talking about. So the project was SuperStream, which is a big legislative change that has occurred in the superannuation industry over the last few years. What it says is all superannuation funds must now communicate electronically, and they must process rollovers and contributions from their members within 3 days. Which, if you're used to dealing with software, might sound like a long time, but if you're used to dealing with superannuation, it's actually a very short time, and it's a big change for them. But that's not really the story of functional programming at IWF. The story is, this is roughly what we built, and there's not that much interesting about it. In terms of business software, it looks fairly familiar to most people, I would guess. So you've got some JSON, you've got some HTTP, you've got some FTP server, you've got some XML communication. You're passing data around between a bunch of different services and transforming it from one format into another. You're talking to databases, you're talking to file systems, you've got a web user interface. There's really nothing particularly out of the ordinary here. It's an ordinary business project. So the thing that is slightly out of the ordinary is there were real deadlines. The legislation meant that by a certain date you must be processing this type of communication. And if you didn't do that, then there were actual financial consequences for your firm. So we went through phase 1 of this project, the only one that didn't have a deadline. And we found a fair bit of pain in what we were doing, as you often do in software. And we knew we had a deadline coming up in July 2013. That's the end of phase 2 that you can see there. And we had a bit of time to think before we started that phase of the project. So with our thinking time, as you can probably guess from the topic of this talk, we thought about functional programming. But why would we even consider functional programming? Well, everyone that I speak to about functional programming says one of the big advantages is that it's easy to reason about. That's obviously a little bit subjective. Some people would say that object-oriented programming is easy to reason about. But really what those people who say that functional programming is easy to reason about are talking about is the fact that it's simple. Simple has a definition. It's an objective definition. It means that you're doing one thing. So as Ken was talking about, the function has one responsibility. It takes input, it gives output. It doesn't mutate state in the middle, hopefully. And therefore, when you run the function over and over again, you get the same result. So, as I said, immutable state and hopefully no side effects. That allows you to reason about what that function is doing much more easily and therefore test it much more easily. So simple is the big thing. That's the whole reason that we're doing this, the whole reason that we're thinking about it. The best explanation that I've seen for why you should do that and why it is simple is Rich Hickey's. He's the creator of Clojure, and this is his talk, but it's not Clojure specific. If you are considering functional programming as a paradigm, I would encourage you to watch that talk and see what he has to say. So, especially on the project that we were doing, it's quite obvious to see that we're taking data from one place, we're transforming it, we're putting it into some other places, and then the same back again. If you look at that picture, there's input, there's transforming, and then there's output. It very obviously maps to mathematical functions. So this is kind of why we were thinking, especially on this project, this is the perfect way, the perfect time to introduce functional programming. And then we also, there was that pain that we experienced in phase 1, where we were writing Java, but we were bending Java a lot to our will. This is Guava, which is a functional library for Java. I don't know if you can make sense of that, but it's basically doing transformation. Some people in our team already had tried Clojure, and that got us wondering, maybe we could do something like this instead. So we had this suspicion that there was a better way of doing the program that we needed to do. We experienced our pain, we had some thinking time, and we said, how can we be sure? How can we A, convince ourselves that doing this in a functional way is a good idea, and B, convince others? So it was a little bit of time. We thought we had a little bit of time to run this experiment. So we engaged in a pseudoscientific experiment where we evaluated the 3 languages that we thought we might be interested in on these criteria. So the languages were Java, Scala, and Clojure. The only reason for that is they all run on the JVM. IWF is pretty tied to the JVM at the moment, so using a JVM language made things easier. If you look at these evaluation criteria, they might look familiar. They're pretty standard evaluation criteria for starting a new project. These are things you always want. So we had these 3 weeks in which we could try to work out what the best way to go was. We had the 3 languages. We knew roughly what we needed to do for the second phase. As I mentioned, we were talking XML, we were talking FTP, where there was a bit of SOAP in there was HTTP, JSON, talking to databases, updating things on the file system. So we knew roughly the functionality that we needed. So we took this thin vertical slice, which is what is represented by that green box up there. We took our 9 developers, and we started trying to do that in these 3 languages in parallel. So we were rotating daily between these pairing arrangements so that everyone got to see all the languages. And we were trying to work out what was good. So we used some metrics. We started out thinking we'll be really scientific. We'll use objective measurements. We'll take every 15 minutes and we'll work out what we've been doing for the last 15 minutes and we'll write it down on a big spreadsheet. We'll see at the end, objectively, what's the best way to go, because if we spend lots of time doing useless things, then that's not a good way to go. That didn't really work too well, in my opinion. The more important thing was the overall gut feel and the other subjective measures that we talked about. So after 2 weeks, we looked at our gut feel. There were a bunch of other metrics we collected as well, which I haven't shown you here, but this really is the summary. As you can see, Java they all kind of waver a little bit, but it ends out that Clojure is at the top and Java is at the bottom at the end of 2 weeks. So since we knew that we could do this in Java, and we knew we were going to choose Clojure over Scala at this point, we dropped Scala. We dropped Java as well. We just checked in the final week whether we could do what we needed to do in Clojure. And you see down the bottom there's voting. Obviously someone abstained because there's only 8 votes there. But the majority of us were in favour of Clojure. This scoring is the average of all the developers, and the gut feel is rated between 2, where 2 is feeling really good, and -2, where -2 is feeling really terrible. And remember, this graph represents our team doing our specific problem over 2 weeks. So it doesn't say Clojure is better than Scala. It says, given that what we knew and what we were doing, we found Clojure a more enjoyable experience. So there's a little bit of red there, which is where we went back to Java for a little bit, and then we actually went ahead and did it in Clojure. And I guess everyone wants to know whether this was successful, right? So, I mean, yes, we finished ahead of schedule. We had very few defects. We were one of the first funds into testing. We were helping our provider to fix their bugs because we didn't have any of our own. And that's all good. But we can't say for sure that that was due to Clojure. That might just have been because we had a really good team. So I can't say for sure that functional programming made this success. However, if gut feel is the best metric we have, I feel pretty good that Clojure was the right choice. And maybe an even better measure would be who's left ThoughtWorks as a result. 2 people have left from this project to go and seek full-time Clojure work elsewhere. The other question that everyone always has about functional programming is, what about the learning curve? Well, yes, there is a learning curve. The more important question is, how do you go about learning? We had a bunch of ways. The most important one isn't even mentioned up here, which is pairing. So the knowledge sharing that we got from pairing, just proliferating that knowledge within the team was, I think, the most beneficial thing we did. Additionally, as you may have guessed by the fact that we went towards Clojure during that experiment, we already had people who knew some Clojure. We didn't have the same level of experience in Scala that we did in Clojure, and maybe that's why we ended up at Clojure. Having said, and that was one of the most important things, was always having that point of call when something got too difficult. As it says down the bottom, you have to be willing to accept that not understanding is going to happen, and it's okay. That's kind of a cultural thing that not everyone is good at, but you need that within your team to do something like this. I mean, that applies to most things that you try to learn. Functional programming is quite a big shift from object-oriented programming, which if that's what you're familiar with, you're going to hit this problem. So the other things, much like Ken's FP guilds, we had weekly Clojures, which was an hour of our work time, where one of us would give a presentation, or we would work through some coding problems, talk about something new we discovered that week. And the experiment itself was kind of a learning exercise, right? So at the end of those 3 weeks of experimentation, I had an infinitely better understanding of Clojure than I did at the start. So if you have the opportunity to do that, that's a good way to get started, I think. And I don't know about you, but learning something new gives me motivation. It's often said that you can't use this project to learn your new thing because this is a really important project. We don't have time to mess around with new languages. But actually, that messing around with a new language, maybe it even increases your productivity, because then the people on your team actually care about what they're doing. They want to learn and they want to get better. So I tried to evaluate what we did here. So Clojure is an opinionated language. It doesn't let you do some of the things that you might want to do, like falling back to object-oriented design. It's a very blanket statement. It does in some ways. But we largely avoided writing object-oriented code. Fairly well accepted advice about Clojure is use macros sparingly. I think we did well in that regard. We had very few macros. Sorry, a macro is a way of modifying code in code. So in Lisp or Clojure, the code that you have is data and can be modified as you go. Macros do that for you. It can make things difficult to understand, so we avoided that. Some people say you shouldn't even use libraries that make heavy use of macros because that makes them difficult to understand. We didn't quite go that far, but that's something to consider. Something that a big mistake we made is we introduced side effects. One of the reasons we introduced side effects is we chose a database library that coupled the creation of your queries with the execution of your queries, which meant that that kind of proliferated, and it's a poisonous concept because if your function has side effects, anything that touches it has side effects. Yeah.
Which library?
Karma. We switched to HoneySQL. The other thing that potentially is a problem is maybe Clojure is not opinionated enough. I mean, it does allow you to do side effects anywhere, unlike Haskell. That helped us with our getting to learn Clojure, but it also caused us to make mistakes. So eventually we kind of reached a similar conclusion to REA, where we tried to move all our side effects to the perimeter. So the core business logic is all pure functions, and then the things that execute the logic sit at the perimeter of your code. As I said, we all have this object-oriented background. And for that reason, we approach testing in a certain way. We have mocks. And side effects mean that you have to keep something like that. So we kind of went down this track where we were following object-oriented design, object-oriented testing to a certain extent. And that really was a waste of time. In retrospect, the approach where you test your functions as pure functions and therefore are able to test more at once is a much more effective way of doing things. So we eventually abandoned mocks. So the interesting thing about all of these points is they all relate to simplicity. That's all we're aiming for, really. So IWF right now, obviously I don't work at IWF right now, but I have spoken to people who are there, and they tell me that these things that were happening when I was there, the microservices introduction and the infrastructure automation and the introduction of functional programming, all kind of play well with each other. And actually having microservices allows you to experiment much more easily. The infrastructure automation facilitates that. And additionally, the teams have become more and more self-organizing as time has progressed. So now, when a team spins up a new service, they have the option of choosing whatever language they like. They don't have the architects telling them what to do. So that has led to, across IWF Melbourne, roughly 50-50 of their services being Clojure and Groovy, and no new ones in Java, as far as I'm aware. So, in conclusion, I have concluded that Clojure is a mature general-purpose language, and I would use it on any of the projects I have previously worked on if I had the chance again. I think most business software can benefit from it. And also, experiments are good. This is how we got to this point, right? The ability to experiment means you can try new things, which means you can make progress and make better software. Having said that, I wouldn't go into as much detail as we did with the metrics next time. The important thing is the gut feel, and if you consider that hearts and minds make decisions, we thought much more about the minds than we did about the hearts. So it's all about convincing everyone and convincing yourself, but that is a lot more to do with emotion than it is to do with logic. If you wish to start writing Clojure, these are my pointers. Not necessarily the same as everyone, but I'm not a book person, so for my suggestions for learning, I would go to clojurecoins.com. It kind of takes you through the different parts of the language through actually writing code. Braveclojure.com is kind of like Learn You a Haskell, which I think is a good explanation of Haskell. This is in progress, but it will be a book at some point. And then tooling, you've got Clojure Toolbox. That tells you what libraries are out there. It's then up to you to evaluate them. These are my choices on the right. The IDE is interesting. Most people who write Clojure use Emacs. But if you're trying to learn Clojure, I would focus on learning Clojure and not learning Emacs. So that's why I've recommended Cursive Clojure. That's all. Thank you very much.